Let's now generate this density maps from the Shanghai Tech dataset. The Shanghai Tech dataset is made of images which are 768 by 1024. So that's why we define this in X and in Y as such. Then we have out X, out Y, which are the dimensions of our output, which happen to be the density maps we've seen already in the slides. So we're going to subsample this from 768 to 96, and then this from 1024 to 128. Now dividing this by 8 gives us this, and then dividing this by 8 gives us this. So it's been subsampled by the same factor, so we have this subsampling factor, which we call, or which we have as in X divided by out X, or in Y divided by out Y. Either way it works. So we'll take this off, and now we go ahead to define the Gaussian distribution which we saw on the slides. This is defined quite simply. We have the mean of the distribution, we have a standard deviation which we define as sigma, and then we set it to this value of 10 by default. Then we have the formula which we saw already, which is this. We shall take this, separate these portions. We have the first part, which is 1 divided by the square root of 2 pi sigma square. So this is the first part, and then the part which takes in the x is this e to the power of negative half times x minus mu divided by sigma square. So basically that's it. Then we add this first dimension right here. Then the next thing we do is now to define a function which generates the density map. So there we go. We have this get density map Gaussian function which takes in the image. It takes in all the points in that image which contain heads, or the positions where we have heads, and then we have this sigma value right here, which is actually the Gaussian radius. So let's take this off. We have this as the Gaussian radius. Set it to be a default value of 2. Take this off. That's fine. Now the role of this Gaussian radius is to determine the number of points which are used in generating for each of the heads its own local Gaussian map. Now if we take this right here, we'll see that if we have this pixel, let's pick this pixel in the center which contains a head, we see that all these different points were used to generate a Gaussian map. If we increase the Gaussian radius, we may have this occupying maybe the whole of this map. Now this is a hyperparameter which is used to define how far each Gaussian map for each head extends. So like in this case, you see that this is its own radius, like this distance from this point to this. So this pixel, if we could actually count the number of pixels, we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'll see that we have 11. So our Gaussian radius in this case is actually 10, not 11. So now our Gaussian radius in this case is, say, 10. And that means that this 10 points contribute in generating this Gaussian map for this head. Now if our Gaussian radius is 5, it means this patch we have right here is going to be smaller. So we're going to have just 1, 2, 3, 4, 5 points. So this blue parts right here will come right to this. This is going to become smaller than what we have right here. Now if we increase this radius to say 20, instead of ending here, we see that we're going to extend right up to somewhere around this. So we're going to have something like this. So that's actually the concept of the Gaussian radius, and it's a hyperparameter which you could actually tune to see whether or how it affects the model. And also in some cases you may make this hyperparameter adaptive depending on how well it behaves, or better still, how well it affects the model's predictions. So that's fine. We have the width and then the height, which is this. We have this as a width and then this as a height of the image. The number of ground truth points is basically the length of this points right here. Now this points, as we said earlier, is simply all the positions in the image, which is this, not in this, all the positions in this image right here which contain the heads. Now in order to bring these points into the reference of this density map, we shall divide all these points by this factor right here. So in this case, we're going to divide all these points by 8, so that we'll leave from this reference to this new smaller reference. We now continue with our Gaussian map generation, and we shall repeat that for each of the points. That's for each of the heads we have in the image. So that's it. We see here we have the points, so we selected, or we pick the first point. For example, we converting this into an integer. Now we get the x coordinate and the y coordinate of the point, or better still, the h coordinate and then the w coordinate of the point, because this is the, if we have an image like this one right here, this is the origin, we have the h axis, and then we have the width axis. So this is the height, and then this is the width. Now this point, for example, is gotten based on the distance from this origin to this given height, and then distance from this origin to a given width right here to look at this point. Now the reason why we have the minimum of the height, the maximum, or the height -1 and then the width -1 is actually because if this point happens to fall exactly at the last pixel h of the image, or last pixel w of the image, then we consider that it's located at a pixel before its actual position. Now once we have this, we go straight into the generation of our Gaussian map using the Gaussian distribution, which we've defined already, which is this. Now let's look at this. Firstly, we have this Gaussian radius, so we have this lane space. Now let's do something like this. Let's print out np.linspace of, say, -4 and then 4. So we're supposed that our Gaussian radius is 4. So in that case, we have that, and then we have now the Gaussian, or rather we have 4 times 2 plus 1. Let's take this off, run this. You see, we're going from -4 to 4. And the reason why we have this is to specify the number of points we shall consider. You see that, yeah, we actually have 9 points. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now without this, we'll have much more points, which we don't actually want to work with. We want to control the number of points we're working with. So let's have this 4 times 2 plus 1. If we modify this, let's take this off, for example, you see we have now 8 points. And now multiplying this, see, that's fine now. And that's exactly what we'll do right here. We're just putting up all those points we're going to use to generate our Gaussian map. Now once this is done, we generate a Gaussian distribution from all these points. So let's take this right here. We now say, for example, we have the Gaussian distribution of this. Run that. You see that we have now this Gaussian distribution right here. Notice that towards the center we have the highest values. We see how if you go from this 1, 2, 3, 4, 5, it actually peaks at this center. That's at the mean, and then it starts to drop back again. And then this is symmetrical because as we had here, we have our mean to be 0 and then sigma 10. So obviously this is going to be symmetrical. So look at this. You notice that this is exactly equals this, this exactly equals this, this exactly equals this, and then this exactly equals this. Now next thing we could do is also to modify the sigma right here. So we have this right here. We say sigma equals let's say 3. We have that. So we see now that we have this also again. We have this highest value 0.13. It starts to drop, 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 drop. Now if we increase these values, say we take 40 values, 40, 40, run it again, you'll see that these values now become very, very small. See, this is practically 0. And now if we go towards the center, like around this, you see, okay, yeah, like let's find that maximum value 1.32. Yeah, this is it right here. So this is the center right here. See, we have 1.32 times 10 to the -1. That's actually 0.13. Now these values which are towards this end right here, you see that they are practically 0. Now let's put this out. So we have something like this, then we have this right here. When sigma is equals 3, notice how 3 steps, that is, if we take the 3 values close to this peak value, you see they are of reasonable magnitude. Here we have, for example, this, and this one. But as from this, like, let's pinpoint this too. As from this going downwards and then this going this way, you see that the values become very, very small up to the point when we get to the 0 right here. Now let's modify the value for sigma to say 2, and now see how this is also going to make even this third value right here become also very small. So we'll put that to 2, run it again. Now let's check this out. You see that this now goes to practically 0.2. Now this is at 0.17, and then from this now we have 0.1, 2, 0.06, and so on and so forth. So unlike previously where we went up to -40, now we even go right up to -88 to show that this drop we had previously now even goes faster. So instead of having that, we now have something like this. So that's it. Now let's take it back to this. We see, as we had seen previously, if our sigma is somewhere like this, let's say this is sigma standard deviation of 3. Now if a standard deviation drops to 2, so it means we are around this, or rather drops to 2, so it means we're gonna have a new, see, we're gonna have something like this now, which is, let's draw it like that. Okay, so we're gonna have something like this now. So it means that in this case now, only very few neighbors around the mean get to have reasonable values. And then if we were to modify this to 10, you see that instead of having this kind of curve, we're gonna have something like this now. So it's gonna be something like this. And this is because in this case we're extending our standard deviation. Let's even take a value of 5. So we match up with those values right here. So let's say 6, for example. So now our standard deviation is 6. So we see that it's going to be something like this. And now this peak value, that is the highest value, is going to be reduced compared to the other highest values we had, because now many of the values are shared with the neighbors. So that's it. Now the next thing we'll look at is the fact that the Gaussian distribution we're trying to produce isn't actually a one-dimensional Gaussian distribution where we have this input x and then we have this output. In this case, we actually have 2 points. So, or rather, we have a point which takes 2 values, which we could say h and w. And so, in this case, it means we have something like this. We have, instead of just having one, say h, we have now h and w. So, if we consider this to be the, let's take this to be the h-axis. So let's do this. We have this as the h-axis, and then this as the w-axis. Now, in this case, instead of having just some 2-dimensional plot here, this is meant to be a 3-dimensional plot. So we're gonna have, let's take this. We're gonna have something like this. And this is such that for every h and w we have its probability distribution, and that's now why when you look at the plot of the density Gaussian map, you have something like this. You have this, you have this, you have this, and so on and so forth. And that's because this is like the x and then the y, and then we have p of xy. So instead of having p of x as we define it, we now have p of xy. But now note that we are going to actually approximate this multivariate Gaussian distribution to be just simply p of x times p of y. So we suppose that p of xy is the same as p of x times p of y. And that's why right here we have this numpy multiplier where we take the x and then we have the y. Now to obtain this y, that's, suppose we take the h and then that's p of h and then times p of w To obtain this, we simply find the transpose of what we got right here. So that's how we obtain this, and then we obtain this Gaussian map right here. So unlike previously where we just had a vector of points, now we actually have a matrix. So let's take this, let's reduce this back to 4. We have this back as 4. Run this again. See, we have this. Let's let this to be G. So we have this as G is equals this. That's fine. We now say print out the multiply of G comma G transpose. Run that, and there we go. So instead of having this, let's print out this shit. So instead of having this 9-dimensional vector for the Gaussian distribution, now we have this matrix right here, and soon we shall plot out this matrix so you see exactly how it looks like. We then move to the next part. Now let's suppose we have this Gaussian radius of 4 right here, just as what we did here. So this gave us this 9x9 matrix for the Gaussian map, which we calculate right here. Now the use of this term is to normalize this Gaussian map, because depending on the number of points we decide to work with right here, we may have a situation where this Gaussian map doesn't even sum up to 1. So what we do is we take the Gaussian map and then divide by the sum of the Gaussian map values to make sure this Gaussian map has all its values summing up to 1. Let's take this as an example where instead of having this, we have a sum. So we print out np.sum, run it. You see, we don't have exactly 1, but if we divide this, that is, if we take the, that is this sum, like this, take this from this, we divide by itself. Now let's have the np.multiply, which is a Gaussian map itself. We run it, and then we have the np.sum of all this. Anyway, let's separate this. So let's suppose we have this Gaussian map, which is equals this, and then we have this np.sum of the Gaussian map right here. So we have our Gaussian map. We now go ahead to print out the Gaussian map divided by the sum of its values. So there we go. We run this, and then we'll define a normalized Gaussian map. So this is actually a normalized Gaussian map, which is this, and then we print it out. So we have the print. Okay, that's fine. We now np.sum of this normalized Gaussian map. See, we have exactly 1 because we've taken this Gaussian map and then divided by the sum of all the normalized Gaussian map, or the sum of all the Gaussian map values. So that's exactly what we do right here to normalize our Gaussian map. Now once we have this, we are struggling to create a patch on the output image or on the output map. So what we're going to do is, from this 9x9 matrix, which is this Gaussian map, in the case where we're supposing the Gaussian radius is 4, we're going to have 9 points. 4 plus 2 plus 1, that's 9. We saw that already. So we're going to have a 9x9 matrix for the Gaussian map, which we could represent as this, where we have the origin right here. We have 9 steps to the right and then 9 steps downwards. So this forms our 9x9 matrix, which is this square right here. And that's why, as you could see here, we define x left to be 0. So for the at the left position, our x coordinate is at 0. That's this. See our x coordinate right here, which is, because this is our x axis, this is what we're supposed to be our x axis. So this x coordinate right here is 0 in the left position of this square. And then for the x right is the Gaussian map shape 1. Now this Gaussian map shape 1 is 9. So our x right is 9, which is normal, because from moving this way at this point, this position, our x coordinate is 9. And then we'll do the same for our y up. Our y up is actually this, because this is the upper part of our square. So this y coordinate, because our y starts from 0 and goes down to 9. This y coordinate is 0. That's why right here we have 0. And then for our y down, which is this, it's actually equals 9. So that's how we obtain this. Now supposing the point we've selected is at say 3624. So if we go 36 steps here, so this, if we go, let's take this 36, and then we go downward like this 24. So we have the point 3624 we're working with now. If we have this point 3624, now we'll see exactly why we need to do all this right here. And in this case, if we compare this point 1 in this case is 24. So if we compare this h coordinate, that's the height coordinate, with the Gaussian radius, which happens to be 4, if we compare it and we see that this 24 is greater than this, we don't have to get into this. The same for the 36. So we compare 36 is not less than 4, so we don't have to get into this. And then we compare the 24 plus 4 with the width of the density map. In this case, it's not greater than W, so we don't have to get into this, because we're supposing we're having a 96 by 128 density map, 128, where we have the height to be 96 and then the width to be 128. And so as we could see, the 24 plus 4 is not greater than 128, so we don't have to get into this. Again, for this, we have the 36 plus 4 is not greater than 96, so we don't have to get into that. So all this for now isn't very useful, because this patch we have is actually well fitted in our density map. And so in that case, if we have this density map, which initially was made of only zeros as we had defined initially, as you can see right here, what we do is we take the patch and then we simply add it up or stamp it on the density map, as we could see right here. So we take this and then put it up on this density map, so that all the values it gets now, the values we had seen previously, and now occupied. That is all the values which correspond to the position with respect to this point right here, because we're at the point 3624. That's supposing we have the center. What we do now, if we have the center, we also have the center. We now just take this and then fit it such that this center matches up with the center on the density map right here. And so to locate this patch on the density map, we have 0.0 minus the Gaussian radius. In this case, that happens to be 24. So we have 24 minus 4. So we found out this position right here. Up to, let's ignore this max of 0, comparing 0 and this value for now, because as we've seen, this patch actually fits well in the density map, so we wouldn't have any problem. So we ignore the max, we're just focusing on this. So as we've seen, we have 24 minus 4, so we are at the point 20 now. We've looked at this 20 with respect to the height. So, and then up to, let's ignore again the minimum and let's focus only on this, up to 0.0 plus the Gaussian radius plus 1. Now 0.0 again is 24, 24 plus 4 plus 1 is 29. So we're going from 20 to 29. That's for the h-axis. So that's how we look at this. And then for the w-axis, we're going from 0.1 minus the Gaussian radius. Now 0.1 is 36, so we have 36 minus 4. It gives us 32. So instead of having 36 as we had seen here in the center, we start at 32, and then we go up to 32 plus 9. So 32 plus 9 should be 41. So that's how we locate these positions where we're going to take this Gaussian map we had generated right here and then patch it up on the density map. So as we've seen, once we look at these positions, all we do is just to simply add it, as you can see right here. We take the density, the Gaussian map, and then added it on the density map, which initially was value which had values of zeros initially. Now once we have done this, we simply repeat for all the points, and see now that that's how we generate all other points like this. Let's draw this a bit bigger. We have points like this. We even have points close to this, so we'll draw something like this. And you now notice that this regions where we have this intersections, now we create points with higher values or relatively higher values compared to all other points where maybe there's so many spaces. So this translates to the fact that when there are many people around the same region, those values have higher magnitudes as compared to other regions where the people are actually spaced out. And once we have this, we will notice in the density map that those regions appear more yellowish as compared to the other regions. Now let's suppose a situation where these conditions are verified, that is the edge conditions. That's supposing we have this patch but which falls at a point, for example, let's maintain the 36, but we're falling at a point. Let's make this small, so we're gonna, if we maintain 36, then we like go right up towards the end. So if we go towards the end, we'll be at say 94. So suppose we are at the point 94. Let's have 94. So we have 36, 94 right here. So instead of 36, 24, so see now we have 36, 94. In this case, if we get into this, we'll see that everything is okay. We have our point 1, which is 94, which is greater than the Gaussian radius, so we don't have to get into this. Our 36 is greater than the Gaussian radius, we don't have to get into this. But then the point 1, which is 94, plus the Gaussian radius, which is 4, is greater than the width, which is 96. 94 plus 4 is 98, which is greater than 96. Even in the case where it was 92, we have 92 plus the 4 will give us 96, which will be equals, as we could notice here, this is equals, this was strictly, this wasn't strictly, this isn't strictly. So in this case, we will see that we have to get into this. And the reason why we'll get into this is because if we are at a point, say 94, that's we around this, 36, 94, we are at this, it's impossible for us to draw this box where we go 4 steps below and then 4 steps above, like in this case where we had this 1 pixel here, we went 4 steps below, went 4 steps above, 4 steps to the left, 4 steps to the right. Here we can't move freely like that because we had 94, so it's left just 2 steps. The remaining steps are out of the density map, and so that's why we need to get into this, so that we readjust this wide down position right here. Now we made a slight error. This isn't this way. This is actually 94, 36, because we decided to fix this height, this width, and then we work in the height direction. So this is 94 since we have the instead of height width for a point. So this is how we look at the points. So yeah, we have 94, 36 instead. So we'll get back to this. To fix this problem right here, what we'll do is we define our wide down such that instead of having to go from 0 to 9 and 0 to 9, we're gonna crop this at a certain point such that we may go to from 0 to 9, and instead 0 to 9, now we instead go from, say in this case where we have up to 94, we go from say 0 to a value like say 7, such that we now show that going from 0 to 7 and then yeah from 0 to 9, so we're gonna have a 9 by 7 matrix now will permit us, so 9 by 7 instead of 9 by 9 will permit us patch this up on the density map without having any error. And so to obtain this value of 7, basically that's what we do. We have the shape 9 minus the radius plus the 0.94 minus the height minus 1. So with that, we'll see how to deal with this edge values which are around this edges, around those edges, and all this. Now once we're done with this, we also make sure that the minimum height value, because we're having this density map, the way it's structured is such that we have the, let's call this density map dm. So we have the dm, which takes in y mean, or rather h mean, takes in h mean to h max, and then w mean to w max, so that it could come up with this squares we've seen right here. Now in some cases we may have h mean which is negative, or h max which is greater than the height of our density map. So that's why we have this here, where we try to take, in the case where we have a negative value, we're going to pick the value 0, and here in the case where the value is greater than the density map's height, we're going to pick instead the density map's height, so that we don't go out of the density map. And it's the same for the width dimension. Now after converting some of the edge points, or after reducing the edge Gaussian map shapes in order to fit in the density maps, we now have to renormalize our density map. So we have this, where we take the density map and then divide it by, or rather the density map now is itself divided by the sum of the density map divided by the length of the points, or by the number of points we have in our data set for this particular density map. So once we have this, now we could return the density map, and then we could go ahead and test the generation of our density maps. Now let's look at this. We have the image we're going to work with, or the folder for the images. We have the folder for the maps. We pick out an image 1. We have this particular image right here which we've selected. We use a load image from TensorFlow, image to array from TensorFlow, and now we normalize this image, which we put in this variable x, and then we could show this. So let's comment this part, and then let's take this off. We need a plot show, run that. Okay, so this is the image in question. You see it goes from 0 to 768 in the height dimension, and then the width dimension goes from 0 to 1024. We had defined this previously right here. Now once we have this, we now go into the map itself. So let's take this, and to load the map information we use scipy and its load mat function. Now this load mat function is capable of taking this files with extension .mat and then extracting this information from it. So once we have this, we could print out this mat. So let's print out the mat. For now, again, let's uncomment here. We'll print out the mat, and that's fine. So we'll look at these values. We see that this is actually a dictionary which has several keys and values. We have the header, this is value. We have the platform key and its value, created on its value. Then we now have the information we actually need. So this is the image info, and now this is the array we want to work with. So see that this is actually the exact information we want to work with, because we're interested in these points. As we've seen here, we're just basically extracting the points from our met file, which is this. So that's why you see it right here. We specify this image info. See, we specify this image info, so we get that array. Now let's plot out, let's print out the image info. So if we print this out, we have mat of image info. Now run that. You'll notice that we don't have this other parts of our dictionary. Now we only have this again here. To obtain the simple array, which is made of just the points, so we simply have this right here. So we have to pick out this position. So if we have this, you see, we now have just this, which now contains all our points, on which we could pass into this for loop right here. Now that's what we have. We now need to convert these points into the new dimension. Recall that the images come as 900 and no, rather 678 or 68 by 1024. So we need to convert this into 96 by 128. So for every point to do this conversion, we need to divide, for example, this 32 by a certain factor. That factor happens to be 8, because to live from this to 96, we need to divide by 8, and from 1024 to 128, we need to divide by 8. So that factor happens to be 8, and that's exactly what we had defined previously here, the subsampling factor. So instead of having just the points, we subsample them, or subsampling factor. So that's it. And now we're ready to pass this points into this get density map Gaussian function. So that's it. We now take this off, and then we'll plot our density map. So we'll take this, we have that. Notice how this initially had values up to 10,022, but now we have to modify this such that it is restrained from going above 128. Let's test this now. Run this. You see, if we take the point where we had, okay, let's print out those points instead. We have points. Take this off. That's fine. So now we see we go up to 119 and so on and so forth, 127. This should be that 10,022. So that's it. Now once we have this, we have our image, and then we have this to say got okay. So let's modify this now. Instead of sigma, we should have the Gaussian radius. Gaussian radius. So that's it. Now let's take off these points. Running this now, we obtain this Gaussian map right here, or this density map right here, made of this different Gaussian maps. As you could see, we have this image. Notice that this portion where there are no heads, you see it's empty. Then that's it. We could also test with the image we had in the slides. So run that, run this. Oh, we've put a break, so let's take this off. So we have that. Let's take this off now. Run again, and we're fine. So this the image we had with this density map from the slides. We could go ahead and modify the Gaussian radius. Let's take a radius of say 50. You see that this is what we obtain now. Let's reduce this to 20. So you see how it changes slightly. See, reduce this to 10. See, so that's basically it, because for every point now we have less values compared to when we had say 50. With 50 we have 100 values to represent just one point. That's why the Gaussian map looks like this. Now let's put this back to say a value of 10. So that's it. Now let's modify this sigma value. That's the standard deviation. Let's take the standard deviation to be, for example, 2. Run this, and there we go. So we see that reducing the standard deviation makes this more circular, since only points very close to the actual point have reasonable values. We then conclude with a data generator, which takes in the images, the maps by size, subsampling factor. Now from this, we're basically repeating what we've done already right here, where we pre-process the image and then we have our values, or we append this into the X list. So basically we have this image which we append to X, and then we have the density map which we also append to Y. Then we convert this to tensors, and then that's the output. So that's it. We now have the train images which we define, the train maps. Then finally we have our train generator right here.